Good afternoon, everyone. So, we were looking into the solution of partial differential equations in the first example we have taken about for the Cartesian coordinate, and we talked about the parabolic partial differential equation, solution of parabolic partial differential equation using different types of boundary conditions, homogeneous, non-homogeneous, and one dimensional, two dimensional, three dimensional, and we have covered the parabolic partial differential equation extensively, because in chemical engineering applications most of the transient problems are expressed in the form of parabolic partial differential equations. Next, we talk about the solution of elliptic partial differential equation. These conditions are also quite prevalent, these governing equations are also quite prevalent in chemical engineering applications, because the elliptic partial differential equations correspond to the steady state operations, multidimensional steady state operations. Now, we will be looking into the one type of partial differential equation, that will be the hyperbolic partial differential equation, and we will be solving a basic problem, and we have seen enough of the actual problem where there are lots of many sources of non-homogeneities are present, and we have to break down the problem into sub problems considering one non-homogeneity at a time. Also, when you will be having a zero initial condition, homogeneous initial condition and non-homogeneous boundary condition, for that problem again you have to divide that problem into two sub problems considering one non-homogeneity, one time dependent part and one time independent part. Then you redefine the ill post problem into well post problem, and the initial condition of the well post problem will become the steady state solution with a negative sign attached to it, and its all boundary conditions they become homogeneous. So, we have looked into the elliptical partial differential equations, parabolic partial differential equations. For the sake of completeness, I will be taking up hyperbolic partial differential equations, but please remember, in actual mainstream chemical engineering processes, the occurrence of hyperbolic partial differential equations are not quite common. They in some special fields they will be occurring. So, for the sake of completeness, we will be looking into the solution of hyperbolic partial differential equations by using separation of variable, and we will be talking about a well post problem only. The ill post problem can be tackled the same way we have done exactly earlier. So, let us consider del square u del t square is equal to del square u del x square is the governing equation, where the domain x lying between from 0 and L, and domain t is of course between 0 to infinity, t is greater than 0 always. Now, what we do, we require to have two boundary conditions on t, and two initial conditions on t and two boundary conditions on t. On x, the boundary conditions are at x is equal to 0, u is equal to 0, at x is equal to L, u is equal to 0. So, these boundary conditions are homogeneous, and we require to have two initial conditions, because it is ordered 2 with respect to t. So, at t is equal to 0, we define u is equal to some function, let us say some prescribed function of x, and at t is equal to 0, we define del u del t some prescribed function of x. Please remember and note that these two boundary conditions are specified on the same boundary. So, therefore, they are known as the Cauchy boundary condition. Now, although these two boundary conditions are homogeneous, we need not to split it up. Splitting up, that means breaking down the problem into sub problem, is not required, because these non-homogeneities occur at the same boundary. occur on same boundary. So, we treat this problem as a well posed problem, because if you just look into the nature of this problem, if you look into the initial and boundary conditions, both the initial conditions are non homogeneous. If you remember whatever we have discussed about the well posed problem and ill posed problem earlier, is that if the boundary conditions are homogeneous and the initial condition is non homogeneous, then the problem is defined as a well posed problem. When the initial condition is homogeneous and one of the boundary condition becomes non homogeneous, then the problem becomes ill posed problem. So, therefore, this problem where the initial conditions both are specified and boundary conditions are homogeneous, then this is a well posed problem. So, we have already seen that for a well posed problem, we can directly use separation of variable solution. Okay. So, what we do next, we consider that u is a product of two functions which will be entirely function of time and another is entirely function of space. So, if you substitute this in the governing equation, this becomes x d square t d t square is equal to t d square x dx square. So, this becomes 1 over t d square t dx square dt square is equal to 1 over x d square x dx square. Now, the left hand side is a function of time only, the right hand side is a function of space only. They are equal and they will be equal to some constant. Again, if this constant is positive and 0, you will be landing up with a trivial solution. So, this constant has to be a negative constant. So, therefore, we can formulate the standard eigenvalue problem. Now, both the ordinary differential equations are of order 2. So, which one will be formed in which direction, either in t direction or x direction will be forming the standard eigenvalue problem? It will be, of course, in the x direction we will be formulating the standard eigenvalue problem, simply because the boundary conditions are homogeneous in that direction. So, we form d square x dx square plus lambda square x is equal to 0, and the boundary conditions will be at x is equal to 0, capital X is equal to 0, at x is equal to 1, capital X is equal to 0. So, this is a standard eigenvalue problem. Problem with homogeneous boundary conditions. So, therefore, we know the solution of this problem. Lambda n are the eigenvalues n pi, where n is equal to 1, 2, 3 up to infinity, and eigenfunctions are sine functions C 1 sine n pi x. So, we solve the spatial part completely, we get the eigenfunctions. Now, let us look into the time varying part. If we look into the time varying part, this becomes 1 over t d square t dt square is equal to minus n square pi square. We put it lambda corresponding to n. So, t will be replaced by, we consider t as nth solution. So, t subscript n corresponds to nth eigenvalue. So, this will be d square t n d t square is equal to plus n square pi square t n is equal to 0. If you look into the solution to this problem, again the characteristic equation will be m square plus m square is equal to minus n square pi square. So, plus minus I n pi will be the solution. So, the corresponding equation will be, the solution will be formulated by the combination of sine functions and cosine functions. So, therefore, t n as a function of t becomes C 2 sine n pi t plus C 3 cosine n pi t. Okay. So, right. If you remember, there was a slight mistake, it does not change the solution at all. The x if you look into the original problem was defined as at x is equal to 0, the other boundary was defined at x is equal to L instead of 1. So, we put it x equal to L. So, lambda n becomes n pi by L and x n eigenfunctions become sin n pi x by L. So, therefore, we will be having the eigenvalues as n pi by L and eigenfunctions as sin n pi x by L. Okay. So, we will be getting the corresponding solution nth solution, that will be nothing but multiplication of T n and x n. So, this will be C 2 multiplied by C 1. So, it will be C n sin n pi x by L multiplied by C 2 sin n pi t. So, this will be okay, it does not matter, plus C 3 cosine n pi t. So, the solution will be C 2 n, C n and C 2, it will be multiplied, new constant will be C 2 n sin n pi x by L times sin n pi t and plus C 3 n is sin n pi x by L cosine n pi t. Now, we have two constants to be evaluated. So, this is the nth coefficient, nth solution. Now, the solution u will be composed as a linear superpositions of all the solutions. So, u will be nothing but linearly superposed summation of u n is equal to 1 to infinity. So, u is x t, it becomes summation of C 2 n sin n pi x by L sin n pi t plus summation C 3 n is equal to 1 to infinity sin n pi x by L cosine n pi t. Now, only two things, the complete solution is ready, the two constants C 2 n and C 3 n need to be evaluated. Now, the constant these two constants will be evaluated. If you remember, we have in the original problem we had 4 boundary conditions, 2 conditions on t is equal to 0 and 2 conditions on x. Now, we have already utilized the 2 boundary conditions on x and we arrived at the solution of corresponding the eigenfunction sin n pi x by L. Now, we will be utilizing the leftover 2 initial conditions. These were at t is equal to 0, u is equal to sum of some function, some prescribed function of x, or it may be a constant as well, u 0 1. So, if we put in generally some constant function of x f x. So, f x will be is equal to, when I put t is equal to 0, this part becomes 0, the whole equation becomes 0. So, only C 3 n will survive, summation of C 3 n sin n pi x by L and cosine 0 becomes 1. So, we have now we can estimate the constant C 3 n by multiply both sides by sin m pi x by L dx and integrate out over the domain of x from 0 to L. So, f of x sin m pi x by L dx from 0 to L and summation C 3 n integral sin n pi x by L sin m pi x by L dx from 0 to L. So, if we open up this summation, all the terms will vanish because of the because of the orthogonal property of the eigenfunctions, only one term will survive, that will be C3 n when m becomes equal to n sin square n pi x by L, okay, integral dx 0 to L, and we know the solution of this will be 2 by L in this particular case. So, C3 n we can obtain. So, this becomes L by 2. Okay. So, this becomes L by 2. So, we will be getting C3 n multiplied by L by 2 is integral 0 to 1 0 to L f of x sin m pi x by L dx, and changing the index from m to n, we will be getting C3 n is equal to 2 by L 0 to L f of x sin n pi x by L dx. Now, for if f x is a known function, we can integrate it out. If f x is constant, let us say u 0, then C3 n will be nothing but 2 u 0 by L 1 minus cosine n pi by L divided by n pi by L. So, L will be cancelled out. So, it will be 2 u 0 over n pi 1 minus cosine n pi by L. So, that will be the constant value of constant C3 n. Similarly, the value of the constant C4 n can be evaluated from the other boundary condition. For that, what we have to write? We have to write down the expression of u3 u x t. U x t was summation of C2 n sin n pi x by L sin n pi t plus summation C3 n sin n pi x by L cosine n pi t. So, if you remember, the other boundary condition is from other boundary condition was at t is equal to 0, del u del t is equal to 0. Okay. So, we del u del t is equal to some function, right, g of x. If you remember, for a general case it is g of x, it may be a constant as well, it may be u1 if it is a constant. Now, then we can evaluate this, we differentiate this expression with respect to t. So, what we will be getting is del u del t is nothing but summation C to n n pi, okay, sin n pi x by L cosine n pi t, okay, differentiator of that. So, n pi has taken out, plus summation of C3 n sin n pi x by L cosine n pi t. So, minus n pi will be there into sin n pi t. Now, we put the boundary condition at t is equal to 0, del u del t will be is equal to g of x. So, g of x, when you put t is equal to 0, this term, the second term will vanish, but the cos 0 becomes 1. So, C2 n will survive, C2 n n pi sin n pi x by L cosine n pi t. Now, we multiply both side by cosine n pi t will be 1. So, we are putting t is equal to 0. So, it becomes cos 0. So, this cosine n pi t becomes 1. So, we will be getting this equation. We multiply again by both side by sin m pi x by L dx and integrate over the domain of x from 0 to L, and we carry out the open up this summation series. All the terms will vanish because of the orthogonal property of the sine functions. Only one term will survive, that is m is equal to n. So, therefore, you will be getting integral g of x sin n pi x by L. I change the index from m to n dx from 0 to L is equal to C 2 n into n pi sin square n pi x by L dx integral 0 to L, and this will be L by 2. So, C 2 n into n pi L by 2. So, you can evaluate C 2 n by 2 divided by n pi times L integral 0 to L g of x sin n pi x by L. So, we will be getting the you will be evaluating the C 2 n value. So, one can get the C 3 n as we have done earlier. We can get the C 2 n if we know the functional form of g x, either constant or maybe something x or x square e to the power k x. We can evaluate this integral by integration by parts. So, that will completely solve and specify the problem. So, that way a basic problem or a well posed hyperbolic problem can be solved, and we are almost at the end of the solution of partial differential equation in the in Cartesian coordinate. What we have done? We have taken up all sorts of boundary conditions, homogeneous, non-homogeneous. We have looked into the different types of differential equations like parabolic, hyperbolic, elliptical, and there are various variants. Now, we will be moving over to the Cartesian polar coordinate system. We looked into the Cartesian coordinate system. Now, we will be looking into the polar coordinate system, cylindrical polar coordinate system. So, this is cylindrical polar coordinate system. These will be quite popular, they will be apparent whenever you are solving a cylindrical polar coordinate. For example, flow through a pipe, conduction in a pipe, may be solid, may be annular. That means, whenever the geometry is cylindrical in nature, the for cylindrical geometry, these equations are prevalent. Okay. So, we will be solving a transient heat conduction problem in one dimension. Transient one dimensional heat conduction problem. So, this becomes del u, the governing equation becomes del u del t is equal to 1 over r del r del u del r. Okay. So, this is the governing equation. This is transient, one dimension in time, another dimension in space, and del 1 by r del r del r is the operating condition, is the operator in the cylindrical polar coordinate system. Now, the boundary conditions, we specify the initial condition and boundary conditions. The initial condition is that at t is equal to 0, u is equal to either constant or it will be a specified variation or function with respect to r. The boundary conditions are at r is equal to 1, that means these are all non-dimensional term. R is equal to 1 means it is on the wall. Okay. R star is equal to r by capital R. So, it is on the wall. You will be having a constant heat, constant temperature condition, u is equal to 0. So, and the other boundary conditions need not to be specified. You do not know in fact the other boundary is at r is equal to 0. So, what will be the condition at r is equal to 0? The condition at r is equal to 0 is that the temperature must be a finite quantity. That means it is bounded. So, we have the if you look into this problem, that u is finite is basically we do not have any specification on this boundary. This boundary we are assuming that is apparent from the physics of the problem. So, this is known as a physical boundary condition. So, if you look into the original problem would have been rho Cp del T is equal to k by r del r del u del r. So, del u del T is nothing but alpha by r del r del T del r. Now, the boundary conditions and initial conditions were at T is equal to 0, temperature T was equal to T naught, at r is equal to capital R, T is equal to T1, and r is equal to 0, T was equal to finite. Now, we make everything non-dimensional, we make the non-dimensional temperature as T minus T1 divided by T1. So, the boundary condition becomes this boundary condition at r is equal to 1 becomes homogeneous, and the initial condition will be non-zero initial condition. And since we do not have any control over this boundary, so it will be replacing it by a physical boundary condition, and so therefore, the problem becomes a well posed problem. Okay. The non-zero initial conditions, that means non-homogeneous initial condition, and and homogeneous boundary condition at the boundary at r equal to 0, this becomes finite or bounded. So, we solve this problem by using separation of variable. Consider u is a product of two functions, one is completely entirely a function of time, another is entirely function of space. So, we put it there, we put this equation, the governing equation, this becomes r dt dt is equal to T over r d dr r dr dr. So, you will be getting 1 over T dt dt is equal to 1 over r r d dr r dr dr. Now, the left hand side is completely a function of time, the right hand side is entirely a function of space, and they are equal, they will be equal to some constant, and this constant can be 0, it can be positive, it can be negative. So, let us say plus alpha lambda square, and this will be minus lambda square, we put everything in lambda, let us say. So, if the constant, so we examine these three cases and look into the r varying part. So, case 1, constant is equal to 0. So, therefore, it becomes r r d dr r dr dr is equal to 0. So, we will be having so we can solve this problem, and let us look into the boundary condition that at r is equal to 0, capital R is finite, at r is equal to 1, capital R is equal to 0. So, it must be satisfying the boundary conditions on r on the original problem. So, what will be this equation? R will be cancelling out. So, one integration will give you r dr dr is equal to C1. So, this becomes dr dr is equal to C1 by r, and solution becomes C1 ln r plus C2. Okay. So, we have these two this is the solution where C1 and C2 are the corresponding constants of integration. Now, when you put at r is equal to 0, capital R is finite, then this term becomes a problem. Oh, okay. So, this becomes infinite. So, the solution is the corresponding constant must be equal to 0 in order to have a finite value of r. So, at r is equal to 0, capital R is finite, that simply leads to a condition that C1 is equal to 0, because it cannot be, R cannot be infinite at any location. not even r is equal to 0. So, the associated constant must be equal to 0. So, therefore, to have r bounded. So, r is equal to r, solution is a constant solution. Now, let us look into the other boundary condition, that at r is equal to 1, capital R is equal to 0. Now, as I said earlier, the solution or the differential equation is valid throughout the whole volume of the system as well as on the surface, but the surface condition, boundary conditions must be valid on the boundary. It need not to be satisfied within the control volume. So, therefore, to make at r equal to capital R is equal to 0, at r equal to 1, that C 2 must be equal to 0. So, the solution is r is equal to 0. So, this is nothing but a trivial solution. Okay. So, that is one in case 2. So, what is this indicates that that means the constant we are talking about, it cannot be is equal to 0. Now, let us look into case 2. Case 2, the constant is positive, constant is plus lambda square. So, we have 1 over r r d dr r dr dr is equal to lambda square. So, d dr of r dr dr is equal to lambda square r r. So, we will be having r d square r dr square plus dr dr minus lambda square r r is equal to 0. Now, put y is equal to, substitute y is equal to lambda r, and then try to simplify this equation, express this equation in terms of y. So, what you will be ultimately getting, I am just omitting couple of steps in between, you will be getting y square d square r d y square plus y dr dy minus y square r is equal to 0. Now, if you look into this equation, you can identify this equation is nothing but the Bessel equation of 0th order. So, this is 0th order Bessel equation. So, the solution is constituted, okay, this is 0th order Bessel equation, but it is a modified Bessel equation, because there is a minus sign there. So, the solution will be comprised of I 0 y and k 0 y. So, therefore, the solution becomes r, a function of y, C 1 I 0 y plus C 2 k 0 y. So, y is lambda r. So, C 1 I 0 lambda r plus C 2 k 0 lambda r. Now, at r is equal to the, let us look into the boundary conditions, r equal to 0, r was bounded, and if you look into the property of I 0 functions and k 0 functions, the k 0 is unbounded, that we have already seen earlier. Therefore, to make this r 0 bounded or finite, these are same, bounded or finite, the associated constant must be equal to 0. So, these indicate C 2 must be equal to 0. So, r of y becomes, y is lambda r, r of r becomes C 1 I 0 lambda r. Now, let us put the other boundary conditions, that at r is equal to 1, capital R becomes 0. So, 0 equal to C 1 I 0 lambda. Now, if you remember, the variation of I 0 as a function of lambda will be some positive, then it is increasing like this. So, I 0 lambda is always positive, it is ever positive function. So, in order to satisfy this equation, I 0 cannot be 0. So, C 1 must be equal to 0. If C 1 is equal to 0, let us see the fate of the function r, this becomes 0. So, again we are going to get a trivial solution which we are not looking for. Therefore, lambda cannot be a positive quantity, lambda cannot be a positive quantity. So, what is left behind is that lambda is a negative quantity. Case 3, lambda is negative, constant is negative, that means it is minus lambda square. So, if you look into the solution of the equation, d dr of r dr is plus lambda square r is equal to 0. So, again we put y is equal to lambda r. So, it becomes y square d square r dy square plus y dr dy plus y square r. So, the form of the equation is the Bessel equation, 0th order, and the solution will be constituted of j 0 and y 0. So, C 1 j 0 y plus C 2 y 0 y. So, this becomes r lambda r is equal to C 1 j 0 lambda r plus C 2 y 0 lambda r. So, this is nothing but r of r. Now, let us look into the boundary conditions at r is equal to 0, y r capital R is finite. That means, if you look into the property of y 0 function, y 0 is infinite at r is equal to 0. So, this is y 0. So, to make it a finite value, the associated constant must be equal to 0. So, therefore, r of r is nothing but C 1 j 0 lambda r. Now, let us look into the use the other boundary condition. The other boundary condition is that r is equal to 1, capital R is equal to 0. So, 0 is equal to C 1 j 0, r is equal to 1. So, j 0 lambda. Now, if you look into the formulation of j 0, the property of the j 0 as a function of lambda, j 0 starts from a positive quantity and it cuts x axis infinite number of time with a diminishing amplitude. So, that means, it cuts x axis infinite number times. So, at every point these are the every location where the j 0 lambda is 0 is a root or the 0. So, these are the solutions or the eigenvalues for this particular problem. So, in order to have a non-trivial solution, C 1 must not be equal to 0. That means, j 0 lambda is equal to 0 and j 0 lambda intersects the x axis, the lambda axis in infinite number of times, and each of the values lambda 1, lambda 2, lambda 3, lambda 4 like up to lambda n, they becomes the eigenvalue. So, j 0 lambda equal to 0 is the transcendental equation roots or zeros of these equations are eigenvalues. So, what are the eigenfunctions? So, we can write j 0 lambda n is equal to 0, lambda n is the nth root of this solution, and the eigenfunctions are r corresponds to n is nothing but C 1 j 0 lambda n r. So, these are the eigenfunctions. So, this proves that in order to have a non-trivial solution, we must be having the constant must be equal to a negative constants, and we will be getting the eigenvalues as the roots of the 0th order Bessel function, and the eigenfunctions are the Bessel functions, eigenfunctions are the j 0 functions. Okay. So, then we will be getting the corresponding eigenvalue problem. Now, we will be looking into a property of these eigenfunctions, the Bessel functions, that Bessel functions are orthogonal to each other or not. So, that we will be evaluating this final constant of using separation of variable, and the solution of this cylindrical polar coordinate system becomes complete. Now, it must be mentioned here that in an actual problem these eigenvalues and eigenfunctions can be evaluated numerically. So, there are standard subroutines like photons, photon recipe of photon recipes in C. In those books there are standard subroutines available. One can get back into those standard subroutines. Those are available in IMSL, those are available in the MATLAB. So, one can get n number of roots of the Bessel function and one can compute the Bessel functions for different values of r, etc. There are recursive formula, etc. all are available. Now, all these things can be numerically done. You need not to write any subroutines. These subroutines are standard subroutines are available online. Okay. So, the alternative method is that at the end of the of any standard heat conduction textbook, or any standard mathematical book, the Bessel functions, the roots of the Bessel equation, Bessel function are computed. First 5 roots or first 10 roots, and various values of Bessel functions are also computed for different values of the arguments. Okay. Next, we look into the solution, the time varying part. If you look into the time varying part, t becomes some constant C2 exponential minus lambda n square t. So, we write t subscript n to denote for the corresponding nth eigenvalue. So, u n will be will be nothing but r n multiplied by t n. So, this will be C 2 multiplied by C 1. So, it will be a new constant C n j 0 lambda n r exponential minus lambda n square t. So, we can construct the complete solution by sum all solutions up by using principle of linear superposition. So, n is equal to 1 to infinity. So, summation of C n j 0 lambda n r exponential minus lambda n square t, n is equal to 1 to infinity. So, that gives the complete solution. Now, in order to get still one thing is incomplete. So, that is the evaluation of this final constant, the Cm, estimation of this constant. If you remember, for the trigonometric functions in the earlier cases in Cartesian coordinate, we use the orthogonal property of the eigenfunctions. Now, in this case we have to prove that the Bessel functions are also the 0th order Bessel functions are also orthogonal to each other. For that, if we can prove that these Bessel functions are orthogonal to each other, then we can use the orthogonal property of the Bessel function and we can estimate the value of C n. For that, let us prove that Bessel functions are orthogonal. The proof goes like this. If you write down the governing equation r d dr of r dr is equal to minus lambda square r r. Now, let us consider lambda 1, lambda 2 are distinct eigenvalues and the corresponding eigenfunctions are j 0 lambda 1 r and j 0 lambda 2 r. So, now, they are the lambda 1 lambda 2 are eigenvalues. We have this equation j 0 lambda 1 is equal to 0 and j 0 lambda 2 is equal to 0. So, because they are eigenvalues, they must be satisfy this equation completely. Now, if you since j 0 and j 0 lambda r and j 0 lambda 2 r, they satisfy the equation. So, first equation will be getting d dr r d dr of j 0 lambda 1 r is equal to minus lambda 1 square r j 0 lambda 1 r, and the second one is d dr of r d dr of j 0 lambda 2 r is equal to minus lambda 2 square r j 0 lambda 2 r. So, we take the inner product of this equation with j 0 lambda 2 r and take the inner product of this equation with respect to j 0 lambda 1 r, and then we subtract it. Okay. So, we multiply this one by j 0 lambda 2 r. So, j 0. So, this is equation number 1, this is equation number 2. We multiply equation 1 by j 0 lambda 2 r dr and multiply equation 2 with j 0 lambda 1 r dr, integrate over the domain of r and then subtract. So, what we will be getting is 0 to 1 j 0 lambda 2 r. So, we multiply this equation by j 0 lambda 2 r dr, multiply this equation by j 0 lambda 1 r dr, then integrate over the domain of r and then we subtract. So, d dr of r d dr of j 0 lambda 1 r minus okay, we just before subtracting we just do it, then we will subtract, then it will be simpler for you. So, this becomes minus lambda 1 square r lambda 1 square, because lambda 1 is constant, it is taken out of integral. So, it becomes r j 0 lambda 1 r j 0 lambda 2 r dr. Okay. So, we just see what you get out of this. So, first function integral of second function. So, first function j 0 lambda 2 r, integral of the second function will be nothing but r d dr of j 0 lambda 1 r from 0 to 1 minus differential of the first function, that means d j 0 lambda 2 r dr multiplied by integral of the second function r d dr j 0 lambda 1 r. Okay. So, 0 to r dr is equal to minus lambda 1 square 0 to 1 r j 0 lambda 1 r j 0 lambda 2 r dr. So, just see this bilinear concomitant term, it will be first term will be j 0 evaluated at r is equal to 1. So, j 0 lambda 2 r will be 1. So, d dr of j 0 lambda 1 r evaluated at r is equal to 1 minus j 0 at 0. So, j 0 at 0 multiplied by r is 0. So, multiplied by whatever it is. So, it becomes 0, it does not matter, minus r d j 0 lambda 2 r dr multiplied by d j 0 lambda 1 r dr is equal to minus lambda 1 square integral j 0 lambda 1 r j 0 lambda 2 r dr from 0 to 1. So, we have already seen that j 0 lambda 2 is 0. So, this whole term becomes 0, it is multiplied by 0. So, whole this term will become 0. So, what is left is minus d j 0 lambda 2 r dr multiplied by d j 0 lambda 1 r dr is equal to minus lambda 1 square 0 to 1 j 0 lambda 1 r J0 lambda 2 r dr. Similarly, from the second equation, if you simplify the second equation, will be this may be equation number 3. From the second equation, we will be getting minus integral dj0 lambda 1 r dr multiplied by dj0 lambda 2 r dr is equal to minus lambda 2 square 0 to 1 j0 lambda 2 r j0 lambda 1 r dr. So, this is equation number 4. Then we subtract 4 minus 3. So, this becomes, if you look into this integral, this becomes the inside the integral, this argument becomes same as this argument. When you subtract, they are in same sign. When you subtract, the same becomes the sign becomes, this sign becomes plus. So, they will be equal and opposite. So, they will be cancelled out. And what will happen on the right hand side? In the right hand side, you will be getting lambda 2 square minus lambda 1 square integral j0 lambda 1 r j0 lambda 2 r dr is equal to 0 from r is equal to 0 to 1. Now, lambda 1 and lambda 2 are not equal, they are distinct. That simply means, in order to satisfy this equation has to be satisfied. That means, inner product of j0 lambda 1 r and inner product of j0 lambda 2 r, they are 0. That means, Bessel functions are orthogonal to each other with respect to the weight function r. So, we write Bessel functions are orthogonal functions with respect to weight function r. So, once we proved this, we are in a position to solve this problem, the transient one dimensional heat conduction problem in cylindrical coordinate. We will be able to complete it. So, if you remember, if you look into the final solution was u is equal to u n was C n e to the power minus lambda n square t j 0 lambda n r, and the complete solution will be constituted by summation of C n e to the power minus lambda n square t j 0 lambda n r. So, we use the initial condition at t is equal to 0, u is equal to u naught or some function of r, generally some function of r. So, this will be f of r is equal to summation of C n j 0 lambda n r. So, we multiply both sides by j 0 lambda m r dr. So, this becomes integral and integrate over the domain of r from 0 to 1 f r j 0 lambda m r dr, and we multiply again both sides by j 0 lambda n r lambda m r dr and integrate over the domain of r from n equal to 1 to infinity. Now, in this case, if you open up this summation, all the other terms will vanish, only the term when, because of the orthogonal property of the Bessel functions that we have proved just few minutes back. So, we will be getting only one term will survive on the right hand side, that is m is equal to n. So, this becomes j 0 square lambda n r dr from 0 to 1, and you will be getting this equation. So, C n can be evaluated by j 0 square lambda n r dr from 0 to 1, from 0 to 1 f of r j 0 lambda n r dr. We change the index m into n and we get the complete solution of C n. So, we evaluate the constant C n and that will give you the complete solution. We put it back there and we can get u as a function of r and t. So, knowing the function f of r, we can evaluate this integral by parts. or one can take the numerical subroutine, maybe Simpson's 1/3 rule or trapezoidal rule to evaluate these two finite integrals to obtain the value of C n for every value of lambda n. So, that completes our solution of one dimensional transient heat conduction problem in cylindrical polar coordinate system. In the next class, I will be taking up a multidimensional problem in the cylindrical polar coordinate system. Okay. So, I stop it here at this class. So, we continue in the next class for solution of multidimensional cylindrical polar coordinate system and how to solve them using separation of variable type of solution. Thank you very much.